Hello again everyone, another biology video from me. Continuing from one I made the other day, we'll call this one Energy Flow Part 2. This time I'm looking at some of the more mathematical aspects of energy flow, as I said before, so you will love that. And also just some of the other implications of the way energy flows through food chains in terms of efficiency of land use and different diets. Right, let's start with a little look at this document. I've sent you all a copy of this, the energy flow additional exercise. Imagine we've got, just improving the focus, there we are, a simple food chain like that. In fact, we're only really looking at, in fact, there are all of these links in it. Now, solar energy reaching the ecosystem, 1.7 million kilojoules. As I mentioned before, plants are actually remarkably inefficient at converting that to chemical energy. The gross primary production, the amount of that solar energy which is converted to chemical energy, in other words glucose, is only that. One of the questions I ask you is to work out the sort of percentage of the solar energy which is converted during gross primary production. It's just that as a percentage of that, and it's low. But even though that's already a very low percentage, of course not even all of that is then available to the animals that eat the plants. Those rabbits don't get to choose from all that, because a lot of that is used in respiration. Only 8,000 odd is actually used to produce new plant biomass. So out of 1.7 million kilojoules, only 8,000 ends up producing new plant biomass. Now what happens to that plant biomass that's available to be eaten? Well, not all of it actually is eaten, of course. Parts of the plant are not eaten. Some plants don't even get eaten at all, but even those parts, even plants that do get eaten, usually it's not the entire plant that gets eaten. The underground bits don't get eaten, sometimes the stems don't get eaten, etc. So in the end, all that the rabbits would consume out of that 8,800, typical value might be 2,400 is consumed by the rabbits. Let's move on down. Just because the rabbits eat parts of the plant containing potentially that much energy doesn't mean that all that energy reaches the rabbits' cells. As we mentioned before, plant food is actually notoriously hard to digest. It's all the sort of nutrients are contained within cellulose cell walls. Now, and it takes a lot of energy to digest the food itself. So even though they ingest 2,400, they would use some of that even simply digesting the food. Plus, they don't actually fully digest it all anyway. Some of it passes out as feces. Quite a large proportion, if it's plant food, passes out as feces. And in the end, the assimilation from eating plants, typically only around sort of 20 to 50%. It could be anything between those. In this case, let's assume it's 840 out of 2,400. Now, of that 840 that is assimilated, this is sort of energy which reaches the rabbit cells and is therefore available to the rabbit. Quite a lot of that is then used in rabbit respiration. The only bit of it that gets used to create new rabbit biomass is only 383 of that 840. The rest gets used in respiration. So in the end, when that hawk comes along wanting to eat rabbits, it's only got 383 left available to it. Now, again, not every rabbit is going to get eaten, and even those that do get eaten, not every part of the rabbit's are eaten. The bones are not eaten, the fur is not eaten. There will be some energy tied up in those parts of the skin. So, in the end, the rabbits and parts of rabbits that are eaten might contain 210. But we've already learnt up here that just because that many joules are eaten doesn't mean that's the energy that is actually acquired. Some of the energy is used in the process of digestion itself. Not all parts of the rabbit are digested, but notice, by the way, that the assimilation rate for eating other animals is a lot higher percentage. That as a percentage of that is a lot higher than that as a percentage of that. That is because animal food is generally much easier to digest. There's no cellulose cell walls. It's a much higher proportion of carbohydrate and fat, so you can assimilate a higher proportion of the potential energy in the food that you eat. Yet again, of course, not all of that, though, goes to produce new hawk biomass. Only that much will produce new biomass. Rest, again, lost through respiration. And as you can see up here, and again, I've sent you this document, you have some follow-up questions there with some lovely maths work on them. Now, there's also, the questions that I've set to you on that sheet feed in to the next few sections on the note sheet, particularly concerning efficiency of land use in terms of food production. Now, if you have a farm with a number of fields, you could grow a load of crops in that field. You might, for example, choose to grow wheat, corn, whatever, and you could potentially yield 100 kilograms of wheat or corn and eat that yourself. You could instead choose to feed that wheat or corn to livestock, and if you do feed it to livestock, wheat or corn you probably wouldn't feed to rabbits, to be honest, but if you were to feed it to cows, chickens, etc., you would only on average get 10 kilograms of meat out of it. And this is, assuming more efficient use than occurs in nature. The sort of energy flow that I showed you on the document is what might occur in a natural setting where not all of the plants get eaten. But here on a farm, you might feed the entire crop to the rabbits. So it doesn't mean that all parts of the plant get eaten, but at least every plant just about gets eaten, the edible parts of it. Basically, you've got a choice of either having 100 kilograms of plant energy for yourself or feeding it to animals and only getting 10% of that energy yourself. And this is, of course, reflected in the types of pyramid I showed you the other day. Again, shown here, you could have 809 kilograms of plant matter or feed it to animals and only get 37 kilograms from it. So if you've got a plot of land, you're going to get far, far more energy by using it to grow crops and eating the crops yourself than using it to grow crops, feeding the crops to animals. You can see the massive reduction in the amount of energy potentially. Now, you can use the points I've made so far to then go on and complete these two sections of the note sheet. Now, I've really pretty much explained those points already. I perhaps, though, ought to just very quickly emphasise the subtle difference, or I wouldn't even say subtle, but important difference in the points that I'm making, because they could appear to contradict each other if you don't think about it. This one is saying, why is it more efficient to eat plants than animals, and this one is saying, why is it more efficient to eat animals than plants? And you could get a bit confused thinking there's a contradiction, so let's just make it totally clear. Right, what we're basically saying is, if you have a plot of land, you could get this much energy by eating the plants that you grow on it, but if you fed it to herbivores and the herbivores, you would only get that much energy. So it is more efficient to use land to grow crops than to produce livestock. The second point actually is saying, though, however, the efficiency of transfer from sort of primary to secondary consumer is a higher percentage efficiency than it is from plants to primary consumers, just because animal food is easier to digest than plant food. Right, a few seconds pause this video and complete several things. If you've not already done so, this exercise here, the energy flow in a food chain exercise. Secondly, just these first two explanations on the note sheet. Thirdly, this question sheet 1.5.10, load of data on the front and questions on the back. This type of sheet, by the way, I'd recommend printing page 2 whilst viewing page 1 on the screen, because you really need to be looking at page 1 to answer page 2. So don't print it double-sided, it makes it awkward. Either only print page 2, or if you insist on printing both pages, print it single-sided so you can view both at the same time. It's my recommendation. Okay, pause this video, come back to me when you've done all that. Right, worth dwelling for a minute or two actually on some further implications of this. I can go through the precise syllabus requirements for your course, but sometimes I like to think, it's good to actually have a look at how what we learn relates to the wider world and look at some of the more interesting aspects of what we're doing and not stick to the narrow confines of the syllabus. It's very easy to appreciate that, using land to grow crops is more efficient than using it to feed animals. But how, what are the implications of that for the real world? Well, as I'm sure you're aware, the world population is still growing, and remarkably, we've actually managed to keep food supply up with the growing population just about, and feed just about everyone on the planet up to this day. Actually, some of the more modern concerns regarding food supply don't sort of relate so much to can we produce enough calories to feed everyone on the planet. Some of the concerns these days are that, wait a minute, as people in the developing world become gradually more wealthy, they are wanting to eat more and more animal-based food. And therefore, this means even a greater amount of inefficient use of land. And the problem is not so much that we can't produce enough energy to feed the planet, is that we can't produce enough energy to feed a large proportion of the planet with animals. And the increasing demand for meat is causing a real squeeze on land use, and ultimately means that food shortages result. I'm actually been highly fortunate in my life to have spent 5 years of my life living in Africa, and what a lot of people don't realise is that our habit for many people in this country of eating large amounts of meat, sort of eating meat every day, even 2 or 3 times a day, some people would eat meat, is highly unusual. this is your typical African meal. Beans, what's often called plantain or matoke in different parts of Africa. It's just basically green bananas, and this stuff here, sometimes called posho or other things in other parts of Africa. This is just made from maize. Actually, totally tasteless stuff. I never liked the stuff myself. The matoke isn't too bad. The beans are often really nice, but no meat in that dish. In Africa, actually, the price of meat reflects its sort of cost of production, if you like, and meat is generally 10 times more expensive than plant food per kilogram. That's because there's no sort of farming subsidies, there's no interfering with the economies of things. Their governments can't afford to give subsidies to anyone, and things cost what their true worth is, to be honest. And you see it in other aspects as well. Nearly everyone gets public transport in Africa, not in part because lots of them can't even afford cars in the first place, but even those that can wouldn't take them over long journeys because public transport is just much cheaper per mile than driving in a car by yourself. It's as it should be. If you've got 50 people on a bus, then the cost of that journey is much cheaper to you than driving in a car by yourself. Somehow in our Western world, that's not the case. Same thing applies to meat out there. The majority of Africans will eat meat twice a year, if they're lucky, Christmas and Easter, and that's it. They will have this the rest of the year. But as they get wealthier, they're starting to eat it far more frequently. Although, interestingly, of course, as demand for meat is going up in the developing world, it's actually going down in the developed world. Vegetarian and veganism are on a real rise in Britain, of course. But it'd be interesting to just, as I say, think for a minute on what the future of food production will be. There is just simply no way that we will be able to produce enough meat to feed, a growing world population, especially if they are demanding a large proportion of their food to be meat. So what do we do about it? Well, tell everyone to eat beans and matoke every day. Not sure that's going to go down well, to be honest. What are the other alternatives? Well, I've sent you links to a few videos on this, actually. One alternative is that more and more people just eat a larger proportion of vegetarian food if they don't become total vegetarians. And, the quality of sort of meat substitutes really is going up these days. So that one option is we all just eat a greater proportion of plant protein, especially sort of plant protein designed to imitate meat for those who need their fix of it. Second option is we continue to eat meat, but we don't get this meat from killing animals. We grow the meat in petri dishes in laboratories from stem cells. Again, sent you a video on this. Third option, again, we continue to eat meat, just not meat as many people think of it. Insect meat. Now, you could stop and think, well, but if insects are primary consumers and you're feeding crops to the insects before eating them, how is that any more efficient than eating cows, for example? Well, it is actually. Insects are far more efficient at converting plant energy into actual or assimilating that into actual animal biomass. You will get far more than 10% of a return from eating insects. Why should that be, you might think? Well, I've sent you a question of that on the questions. I'd rather you have a think about that or look it up for yourselves rather than me tell you, but you will get a more efficient transfer of energy from plants to animals with insects than with cows. And the other thing that will, of course, lead things in this direction is not just the lack of available land to produce enough meat. More and more people are, of course, objecting on moral grounds to the way animals are treated in the whole meat production business. So I think certainly over the future, probably in the fairly near future, the way that meat is consumed and the amount of meat that's consumed is going to change drastically. I mean, we are guilty, some people anyway, in our modern generation, of being very smug, aren't we? When we look back at previous generations and say, oh, look at the casual racism there, look at the homophobia that was about, oh, they kept black people as slaves, etc. It was awful. And we sometimes forget that future generations will probably look back on us in the same way for some of our actions, actually. Right, forgive me, I got a bit sidetracked there. Back to the actual syllabus now, just two very quick points, further points to complete on the note sheet. The final bit is actually fully done for you, just a little bit to add to this. Very quick word of explanation on these. Right. One, food chains don't go on and on forever. At most, they tend to have 6 trophic levels, and most don't even have that many, to be honest. Why is that? Well, it's obvious why. Really, this diagram shows it most clearly. By the time you get to a 5th trophic level, there's basically no energy left to be passed on anymore. Some people can look at this and get slightly confused, say, but don't the animals get bigger as you move up? Shouldn't there be more energy left? You know, after all, an apex predator might be something like a lion and a tiger. Why isn't there anything to be had from eating those? Well, you can make the obvious point, well, you'll have a hard job managing to capture one and kill one to eat it in the first place. But even if you could, then surely you get a really good meal out of a lion, wouldn't you? You would, but there's just hardly any of them. There's just not enough of them. Your average lion might be a bit bigger than your average antelope or buffalo, often not that much bigger actually, but even if they are bigger, there's just so many more herbivores than there are top carnivores because there's so much more food for the herbivores to eat. Lastly, just a quick look at the productivity of different ecosystems. As you can see from this, it's not equal everywhere. Tropical rainforests tend to have more trophic levels in their food chains than anywhere else, just because they've got more energy going in at the bottom. If you've got very little energy going in at the bottom, you might only be able to support 4 trophic levels before the energy's run out. You've got all this, you might manage 6. Notice, by the way, though, that they're not top of the league, tropical rainforests. They are pushed down by algal beds, and it relates back to something I might have mentioned in passing before. Some people sort of talk about tropical rainforests as being vast, sort of carbon sinks, the lungs of the world producing loads of oxygen. Well, they do produce some oxygen and take in some carbon, but 60% of the world's oxygen is actually produced by plankton living in the sea. They are the main source of our oxygen, and by definition they are therefore also the main absorbers of carbon dioxide. They absorb 60% of the carbon dioxide. Right, that is it for me for today. Hope you're all well. Be in touch again next week. Bye for now.